Welcome back to Sleepy Facts. Take a slow breath, relax your mind, rest smarter as we gently drift into tonight's story. If you'd like more quiet stories like this, you are welcome to subscribe. And if there is a topic you want to hear next, just whisper it in the comments. Tonight, we journey through time to discover how humanity learned to capture lightning itself. Close your eyes and imagine a world lit only by fire and sun. A world where darkness fell absolutely when the day ended. A world where the crackle of lightning across the sky seemed like the anger of gods. This is where our story begins. Long before anyone understood electricity, people felt its presence. Ancient peoples watched summer storms roll across open plains. They saw bolts of light tear through clouds. They heard thunder shake the ground beneath their feet. They stood in fields and forests as rain began to fall. They felt the hair on their arms rise in the moments before lightning struck. They smelled the sharp, metallic scent that filled the air after a bolt tore across the sky. They could not know that what they witnessed was the same force that would one day illuminate entire cities. To them, lightning was divine. It was the weapon of Zeus, of Thor, of Indra. It was power beyond human comprehension, something to fear and worship. Pause for a moment and imagine their world. No electric lights to chase away the darkness. No understanding of the forces that move through the air during storms. Just observation, just wonder, just the raw experience of nature's power. The ancient Greeks walked along Mediterranean shores and noticed something peculiar. Picture a Greek philosopher on a quiet beach. The sun is warm, the sea is blue, waves roll gently onto sand. The philosopher holds a piece of amber in his hand. Amber, that golden stone formed from tree resin that hardened over millions of years, smooth and warm to the touch, beautiful in the sunlight. When they rubbed pieces of amber against wool or fur, these golden stones began to attract small objects. Feathers would drift toward the amber as if pulled by invisible threads. Bits of straw would cling to its surface. Dust particles would dance around it. The philosopher watches this with curiosity. He rubs the amber again. Again, the attraction occurs. It is repeatable. It is reliable. But what causes it? They called amber electron in their language. The word meant bright or shining one, referring to amber's golden color. From this simple word, observed on quiet beaches thousands of years ago, we would eventually derive our word electricity. But the Greeks did not understand what they had discovered. To them, it was merely a curiosity, a small mystery of nature, one of many puzzles in a world full of wonders. They wrote about it in their texts. They demonstrated it to students, but they did not investigate further. They did not connect the amber's strange attraction to the lightning that split their skies. They did not imagine that these two phenomena were related, that they were, in fact, manifestations of the same invisible force. How could they? The leap from amber attracting a feather to understanding lightning would require centuries of careful thought and experimentation. It would require tools not yet invented, concepts not yet conceived, languages not yet developed. Centuries passed in quiet darkness. Breathe slowly. Let time wash over you like water. Decades became centuries. Centuries became millennia. Empires rose from dust and crumbled back to dust. Languages evolved and died. Technologies were invented, forgotten, reinvented. The Roman Empire rose. Aqueducts brought water to cities. Roads connected distant provinces. Literature and law and architecture flourished. And then, slowly, the empire declined. The legions withdrew. The roads fell into disrepair. The great libraries were lost or burned. The Middle Ages settled across Europe like a heavy blanket. Knowledge was preserved in monasteries, where monks copied manuscripts by candlelight. Their hands grew cold in unheated scriptoriums. They wrote on vellum made from animal skin. They illuminated pages with gold leaf and bright pigments. Patient work, quiet work, holy work. People lived by candlelight and cook fire. They woke with the sun and slept when darkness came. Their days followed the rhythms of agriculture, planting and harvest, birth and death, feast and famine. The wheel turned slowly. Think of a village at night in medieval times. Houses clustered around a church, smoke rising from chimneys, perhaps a fire burning in the center of the village square. Beyond the circle of firelight, absolute darkness, the kind of darkness we rarely experience in modern times. Darkness thick enough to feel. Darkness where the edge of the village was the edge of the known world. The people in that village knew their neighbors. They knew the sound of each person's voice, the rhythm of each person's walk. They told stories by firelight. They sang songs their grandparents had taught them. They looked up at the night sky and saw stars in quantities we can barely imagine today. The Milky Way stretching across the heavens like a river of light. Constellations so clear they seemed painted on the darkness. Electricity remained hidden in the fabric of the world, waiting to be understood. It flowed in lightning. It created the faint attractions between amber and feathers. It existed in the nervous systems of animals, but no one knew. No one could know. The tools for understanding did not exist. The conceptual framework had not been developed. The experiments had not been conducted. Then came the Renaissance. The word means rebirth, a rebirth of learning, a rebirth of curiosity about the natural world, the age of questioning, the age of looking closely at the world and asking why. Artists studied anatomy. They dissected bodies to understand muscles and bones. They developed perspective to capture three-dimensional space on flat canvas. Mathematicians rediscovered ancient texts. They developed new systems for calculating, new ways of describing motion and force and geometric relationships. And natural philosophers began to experiment. In the year 1600, an English physician named William Gilbert published a book. Its title in Latin was De Magnete, Magnetisque Corporibus, et de Magno Magnete Tellur. In English, On the Magnet and Magnetic Bodies, and on the Great Magnet, the Earth. Gilbert had spent 17 years conducting experiments, 17 years of patient observation. He lived in London, serving as physician to Queen Elizabeth I. But in his spare hours, he worked in his study. He rubbed different materials together. He tested which substances could attract lightweight objects. Amber, yes, but also jet and sulfur and diamond and glass when heated and cooled in certain ways. He built devices to measure the strength of attractions. He used small needles balanced on pivots, watching how they moved when attracted materials came near. He took detailed notes. He drew diagrams. He was systematic, methodical, precise. Picture Gilbert in his candlelit study, windows dark, the city of London quiet outside. He sits at his desk with a piece of amber in one hand and a feather in the other. He rubs the amber with a cloth once, twice, 3 times, then brings the feather close. It moves. Attracted, he writes in his notebook. He tries again with a different material. Tests, records, thinks. He was the first to use the Latin word electricus to describe this attractive force, a word derived from electron, the Greek word for amber. Gilbert worked by candlelight in his study, carefully documenting each experiment, never knowing that he was laying the first stones of a path that would lead to a transformed world. Gilbert understood that the Earth itself was a giant magnet. This was one of his major discoveries. The compass needle points north, not because of some star in the sky, but because the Earth has a magnetic field. The planet we live on generates magnetism. Gilbert could not explain why. That would wait for later centuries. But he established the fact through careful measurement and reasoning. Gilbert died in 1603, possibly from the plague that swept through London that year. But his work lived on. His book was read throughout Europe. Other minds began to wonder. Other hands began to experiment. The candle he had lit continued to burn, passed from one seeker to another. The 1700s arrived. The Age of Enlightenment brought new tools and new thinking. Across Europe, in coffee houses, universities, and private laboratories, people gathered to discuss natural philosophy. They debated, they shared observations, they built networks of correspondence, writing letters that took weeks to arrive, sharing discoveries and questions. Natural philosophers, as scientists were then called, began to build strange devices in their workshops and laboratories. Each new device was a step forward. Each experiment taught something new. In 1660, Otto von Guericke in Germany created the first machine designed to produce electricity. Von Guericke was the mayor of Magdeburg. He was an inventor and experimenter. He is perhaps best known for his demonstration with the Magdeburg hemispheres, 2 copper halves of a sphere that, when the air was pumped out from between them, could not be pulled apart even by teams of horses. He showed that air has weight and pressure, that a vacuum is real. His electrical machine was simpler but equally fascinating. It was a sphere of sulfur, about the size of a child's head, mounted on an axle so it could be rotated. When the sphere was spun and rubbed by hand, it created sparks, tiny lightning captured in a workshop. Imagine von Guericke in his laboratory, the sulfur sphere gleaming dully in candlelight. He sets it spinning with one hand. With the other, he presses his palm against the rotating surface. Friction, heat, and then a snap. A small spark jumps from the sphere to his hand, a brief tingle, a moment of connection with something invisible, something powerful. He does it again and again. Each time, the spark, each time, the evidence that something is being created, something that flows and accumulates and discharges. Others refine the design. In England, Francis Hawksby created a glass globe that produced a soft glow when rubbed and spun in a darkened room. Glass instead of sulfur, a different material, but the same principle. Friction creates electrical charge. Imagine that moment, the first time in human history that human eyes saw electrical light created by human hands. Hawksby darkens his room, all candles extinguished. He spins the glass globe and presses his hands against it. At first, nothing, just the feel of smooth glass under his palms, the faint warmth of friction. Then a glow begins, soft, ghostly, a purplish luminescence that outlines his hands. The light has an otherworldly quality, not like fire, not like sunlight reflected from the moon. Something new, a gentle luminescence in the darkness, a hint of the future. People came to see these demonstrations. The electrical machines became popular attractions. Natural philosophers would set up their equipment in drawing rooms and public halls. They would spin the globes or cylinders. They would create sparks. They would make papers dance in the air. They would charge people's bodies with electricity so sparks would jump from their fingers. It seemed like entertainment, like parlor tricks, but beneath the spectacle, understanding was growing. Questions were being asked. Patterns were being noticed. By the 1740s, experimenters had discovered they could store electrical charge in glass jars. These became known as Leyden jars, named after the city of Leiden in the Netherlands, where they were invented, though multiple experimenters discovered them independently around the same time. A Leyden jar was simplicity itself, a glass container, often a bottle or jar, metal foil coating the inside surface, metal foil coating the outside surface, a metal rod extending from the top into the jar, touching the inner foil. That was all. Glass separating two layers of metal. But this simple arrangement could store electrical charge. When charged from a friction machine, the jar could hold electricity like water in a vessel. It could be carried from place to place without losing its charge. It could sit on a shelf for hours or days, waiting. And when both the inner and outer foils were connected by a conductor, all the stored charge would rush out at once in a bright, startling spark. The first person to accidentally discharge a Leyden jar received a terrible shock. The sudden jolt of electricity through the body, muscles contracting involuntarily. The sensation was unforgettable. Some people refused to try it. Others lined up for the experience. Dozens of people could hold hands in a chain. And when the first person touched the charged jar and the last person touched the outer foil, the shock would travel through all of them simultaneously. They would jump and cry out as one. It was dramatic, it was memorable, and it showed that electricity could be stored and released, that it could move through materials, that it had effects on living tissue, that it was something more than just sparks and glows. It was a force that could be harnessed. People gathered in parlors and meeting halls to witness electrical demonstrations. Showmen charged themselves with electricity and created sparks from their fingertips. They would stand on blocks of wax or glass to insulate themselves from the ground. An assistant would operate the friction machine, charging the showman's body. Then the showman would reach toward a candle flame or toward a member of the audience, and a spark would jump from his finger. Gasps and laughter from the crowd. It seemed like magic, like something from ancient myths where gods hurled lightning. But it was not magic. It was not divine. It was natural. It was repeatable. It could be studied and measured and understood. It was the beginning of true understanding. And then there was Benjamin Franklin. Take a breath. Let his name settle in your mind. Benjamin Franklin, printer, writer, inventor, diplomat, philosopher, a man of countless interests and boundless curiosity. In Philadelphia, in the American colonies, this restless mind turned toward electricity. Franklin was in his 40s. He had achieved success in the printing trade. He published newspapers and almanacs. Poor Richard's Almanac, full of homely wisdom and practical advice. He had time now, time to pursue his curiosities. Franklin conducted experiments in his home. He set up friction machines. He charged Leyden jars. He observed the behavior of electrical charge with the same careful attention he brought to everything. He noticed that some materials seemed to gain charge, while others lost it. He proposed that electricity was not two different forces, but a single fluid that could flow from place to place. Imagine electricity as a fluid, invisible, flowing from object to object. An object with more than its natural amount of this fluid has a surplus. An object with less than its natural amount has a deficit. Surplus flows toward deficit. Balance is restored. It was a simple model, not entirely correct, as later scientists would discover, but it was useful. It made predictions. It explained observations. He gave us the terms we still use today: positive and negative, plus and minus, battery, conductor. These words were Franklin's gifts to the language of electricity. Before Franklin, different experimenters used different terms: vitreous and resinous, attractive and repulsive. Franklin's terminology was clearer, more intuitive. It stuck. But Franklin is remembered for one experiment above all others: the kite experiment, the day he drew lightning from the sky. It was June 1752, summer in Philadelphia, the month when thunderstorms build in the humid air, when dark clouds gather on hot afternoons, when the sky flashes and rumbles. Franklin had been thinking about lightning for years. He had observed its behavior, the way it struck tall objects, the way it sometimes split into branches, the way it could shatter trees and set buildings on fire. He had read descriptions from other experimenters. He had formed a hypothesis. Lightning was electrical. The same force that created sparks in a laboratory was present in thunderclouds. The same force that made Leyden jars discharge was making the sky flash. But how to prove it? He needed to bring lightning close enough to test. He proposed erecting iron rods on high hills, rods that would draw lightning near enough for an experimenter to collect charge from. But such an installation would take time and money. Then Franklin thought of a kite. A kite could be lofted into the storm clouds. A kite on a wet string would provide a path for electrical charge to descend. If his hypothesis was correct, charge from the clouds would flow down the string, and he could test it. He built a simple kite, a silk handkerchief, chosen because silk sheds water less readily than paper, stretched over a wooden frame made of 2 crossed sticks. To the top of the frame, he attached a sharp-pointed wire about a foot long. This would extend up into the air, reaching toward the charged clouds. He attached the kite to a hemp string, and near the bottom of the string, he tied a metal key. The key would collect any charge that flowed down. Below the key, he tied a silk ribbon. Silk, being a poor conductor when dry, would insulate his hand, would protect him from the charge that accumulated on the key. He waited for the right weather. The storm building, clouds dark and heavy, but not raining yet, not lightning yet, the dangerous moment before the storm breaks. Franklin and his son William went into an open field on the edge of Philadelphia. They sought shelter in a small shed, open on one side, where they could stand dry while flying the kite into the storm. The sky was darkening. Wind was picking up. The smell of approaching rain filled the air. They launched the kite. It rose on the strengthening wind. Up, up, the wooden frame and silk handkerchief climbing toward the grey clouds. The string played out. The kite became smaller, a small shape against the vast sky. Franklin held the silk ribbon. William steadied the kite string. They waited. At first, nothing happened. The kite danced in the wind. The string hung down, heavy and damp as rain began to fall. Minutes passed. The storm was overhead now. Thunder rumbled, but no lightning. Not yet. Franklin watched the kite string carefully, the loose threads, the individual fibers of hemp, and then he noticed something. The threads were beginning to stand on end, repelling each other, as if charged. His heart must have quickened. This was it, evidence of charge, but he needed more. He brought his knuckle close to the key, slowly, carefully, closer. A spark jumped the gap, a distinct snap, a brief shock. He pulled back, waited, brought his knuckle close again. Another spark, another snap. The storm itself was charging the kite. Electrical charge was flowing down the wet string, accumulating on the key. Enough charge to create sparks, to give him the same sensation as touching a charged Leyden jar. Lightning was electricity. Franklin stood in that shed in Philadelphia, feeling sparks jump to his hand from a key attached to a kite string, and knew he had proven his hypothesis. The lightning that split the sky and the sparks that jumped from friction machines were the same. One substance, one force, operating on different scales. He collected charge from the key into Leyden jars. He conducted the same experiments he had done with charge from friction machines. The results were identical. Lightning charge and machine charge behaved the same way. Franklin was fortunate to survive this experiment. Lightning is extraordinarily powerful. A typical bolt carries millions of volts and tens of thousands of amperes. If the kite had been struck directly, Franklin would likely have been killed instantly. Other experimenters in Europe who attempted similar experiments were, in fact, killed. Georg Wilhelm Richmann in Russia was struck by lightning during an experiment in 1753 and died. But Franklin's careful design protected him. The charge that reached him was residual charge from the cloud, not a direct strike, enough to prove the hypothesis, not enough to kill. Think of Franklin in that moment, standing in the shed as rain falls around him, thunder rolling across the sky, sparks jumping from a key to his hand, knowing that he has just proven something fundamental about nature, that he has connected two phenomena that seemed entirely separate, that the gods' lightning can be studied, can be understood, can perhaps be controlled. It was one of the defining moments in the history of science, a moment when the natural world became a little less mysterious, a little more comprehensible. Franklin published his findings. Word spread across the Atlantic. His experiment was repeated in France, in England, in other colonies. Each time, the same result. Lightning was electrical. This was now established fact. And Franklin did not stop with understanding. He moved immediately to application. If lightning was electrical, and if electricity could be guided along conductors, then buildings could be protected from lightning strikes. All that was needed was to provide a better path for the lightning than the building itself. Franklin invented the lightning rod, a simple metal pole, pointed at the top, mounted on the highest point of a roof. From the base of the rod, a thick wire ran down the outside of the building and into the ground, where it connected to a metal plate buried in the earth. When lightning struck, it would hit the rod. The rod would conduct the enormous electrical charge safely down the wire and into the ground. The building would be unharmed. No fire, no shattered timbers, no destroyed roof. It was brilliantly simple, and it worked. Franklin installed the first lightning rod on his own house in Philadelphia in 1752. Then on the Pennsylvania State House, now known as Independence Hall. The news spread. Other buildings were equipped. Churches, barns, private homes, each one crowned with Franklin's pointed rod, standing guard against the storm. The lightning rod spread across America and Europe, city by city, building by building. The sharp points of Franklin's invention reached toward the sky. Church steeples that had been struck repeatedly, sometimes burning, sometimes killing the bell ringers, were now protected. Ships mounted lightning rods on their masts, protecting sailors from strikes at sea. Each rod was a small victory over the power of storms. Each one was proof that understanding nature leads to the power to shape our relationship with nature. We could not stop lightning, but we could guide it safely away from what we wished to protect. Franklin's lightning rod was the first practical application of electrical science. The first time that understanding electricity saved lives and property. It would not be the last, but capturing lightning was just the beginning. The late 1700s brought new questions. If electricity could be stored in a jar and drawn from a storm, what else could it do? In Italy, a physician named Luigi Galvani was dissecting frogs in his laboratory. He touched the exposed nerves of a frog's leg with a metal instrument. The leg twitched. Even though the frog was dead, its muscles responded to something. Galvani believed he had discovered animal electricity, a special life force that animated living beings. Another Italian, Alessandro Volta, disagreed. Volta conducted his own experiments. He found that the twitching was caused by two different metals touching the moist tissue of the frog. The metals and the moisture were creating electricity. Life was not required. In 1800, Volta announced his invention, the voltaic pile, the first true battery. He stacked discs of zinc and copper, separated by cardboard, soaked in salt water. When he connected a wire to the top and bottom of this stack, electricity flowed continuously. Not a single spark from a Leyden jar, not a fleeting bolt from a storm, but a steady, reliable current. Imagine holding Volta's battery in your hands, feeling the slight warmth as chemical reactions inside created a flow of electrical charge. This was new. This was something that could be studied at leisure, experimented with day and night. This was the tool that would unlock the next century of discovery. Word of Volta's battery spread quickly through the scientific community. Experimenters across Europe built their own versions. They connected wires to the terminals. They watched what happened. In England, Humphrey Davy built enormous batteries using hundreds of metal plates. He created electrical currents strong enough to heat metal wires until they glowed white hot. In 1809, he demonstrated the first electric arc lamp, two carbon rods connected to his massive battery. When he brought the rods together and then slowly pulled them apart, an intensely bright arc of light blazed between them. It was brilliant, almost blinding. The light had a harsh, white quality unlike any flame, but it required such enormous batteries that it remained a laboratory curiosity. The early 1800s were years of quiet exploration. Experimenters discovered that electrical current flowing through a wire created a magnetic field around it. Magnets could deflect the flow of electricity. Electricity and magnetism were somehow intertwined. Two faces of a deeper mystery. Michael Faraday, the son of a blacksmith in England, became one of the greatest experimental scientists of all time. His story is one of curiosity overcoming circumstance, of native intelligence finding a path despite obstacles. Faraday was born in 1791 in Newington Butts, south of London. His family was poor, very poor. He would later recall days when his family had only one loaf of bread to last the entire week. Education was a luxury they could not afford. Young Michael attended a small day school where he learned to read and write and do simple arithmetic. But his formal education ended when he was about 13. He was apprenticed to a bookbinder, a trade, a way to earn a living. He would learn to sew pages into signatures, to attach them to spines, to create covers from leather and board. It was skilled work, honest work, work that would provide an income. But young Faraday did something unusual. He read the books he was binding. Think about that for a moment. Picture a teenage boy in a bookbinding shop. The smell of leather and glue and paper, his hands learning the craft, but his mind wandering into the pages in front of him. A book on chemistry, a book on natural philosophy, an encyclopedia article on electricity. He read everything. He became particularly interested in books about science. He conducted small experiments at home. Simple things, mixing chemicals, building small electrical devices from instructions in books, testing what he had read. When he was 19, a customer of the bookshop gave Faraday tickets to attend lectures at the Royal Institution. The lecturer was Humphrey Davy, one of the most famous scientists in England. Faraday attended 4 lectures. He took detailed notes. He went home and wrote them up neatly, adding his own illustrations. He bound them into a book. And then he did something bold. He sent the book to Davy, along with a letter asking for employment. Any employment. He wanted to work in science, to be near science, to participate in it. Davy was impressed. When a position opened up at the Royal Institution, Davy hired Faraday as his assistant. It was 1813. Faraday was 21 years old. His life in science had begun. For years, Faraday assisted Davy. He prepared equipment for experiments. He helped conduct demonstrations. He learned by watching and doing. Davy later said that Faraday was his greatest discovery. Eventually, Faraday began conducting his own experiments. He worked in the basement laboratory of the Royal Institution, a room filled with glassware and chemicals and electrical devices, natural light from high windows, a workbench worn smooth from use. In 1821, Faraday was investigating the relationship between electricity and magnetism. It was known that an electric current could deflect a magnetic needle. The two forces interacted somehow, but how? Faraday conducted a simple but elegant experiment. He suspended a wire so it could move freely. He placed it near a magnet fixed in place. When he passed electric current through the wire began to rotate around the magnet. Continuous rotation. As long as current flowed, the wire spun. He had created the first electric motor. Oh, it was crude. A wire spinning in a dish of mercury to maintain electrical contact. It produced no useful work. It was a demonstration. a proof of principle, but it showed something profound. Electricity could produce motion, sustained, continuous motion. Imagine Faraday watching that wire spin, around and around, fed by current from a voltaic battery, the motion continuing as long as the circuit was complete. He understood he was seeing something new, a transformation of electrical energy into mechanical motion. But Faraday did not rest with this discovery. His mind turned to the inverse problem. If electricity could produce motion in a magnetic field, could motion in a magnetic field produce electricity? It took him 10 years to find the answer. 10 years of thinking and experimenting and failing and trying again. 10 years of patient persistence. In 1831, Faraday made his greatest discovery, electromagnetic induction. He found that moving a magnet through a coil of wire created electric current in the wire. Not permanently, only while the magnet was moving. When the motion stopped, the current stopped. But while motion continued, current flowed. He had discovered the principle behind every electric generator ever built. Motion creates electricity. This was the complement to the motor. Motor, electricity creates motion. Generator, motion creates electricity. The circle was complete. Faraday built a simple generator. He mounted a copper disc between the poles of a horseshoe magnet. He attached wires to the edge and center of the disc. When he rotated the disc by hand, current flowed through the wires. He could detect it with a galvanometer, a device for measuring current. The current was weak. It fluctuated as the disc turned. But it was there. Electricity created by motion. Stand for a moment in Faraday's place. In the basement laboratory, the copper disc spinning between the magnet's poles, the galvanometer needle swinging, current flowing, created by your own hand turning the disc. No chemical reactions, no batteries being consumed, just motion and magnetism producing electricity. This was different from Volta's battery. The battery consumed zinc and copper and acid to produce current. The chemicals were gradually used up, but Faraday's generator consumed nothing except the mechanical work of spinning the disc. In principle, as long as you kept spinning, current would flow. Of course, Faraday's simple disc generator was not practical. It produced very little current. The disc had to be spun with great effort. But it proved the concept. Others would improve the design, would build larger generators with multiple coils and stronger magnets, would find ways to spin them with water wheels and steam engines. But Faraday had shown the way. Humanity now possessed two methods to create electricity: chemical reactions in batteries and motion in magnetic fields through generators. Both would prove essential. Faraday worked in his laboratory at the Royal Institution in London. He filled notebook after notebook with careful observations. His notebooks still exist. They are preserved at the Royal Institution. Pages and pages of neat handwriting, diagrams, descriptions of apparatus, records of measurements, the daily work of science. Faraday was not a mathematician. He had little formal training in mathematics. He thought in images, in pictures, in physical intuitions. He imagined invisible lines of force surrounding magnets, lines that filled space, that could be mapped by scattering iron filings near a magnet and watching them align along the invisible lines. He imagined similar lines surrounding electric charges. He thought of space as being full of these lines, a field of influence. His intuitions were profound. His experiments were elegant and revealing, but he could not express his insights in the language of mathematics. He could not write equations. This limited how widely his ideas spread. Scientists of his era increasingly spoke in mathematics. Faraday spoke in words and diagrams, but one man would translate Faraday's insights into mathematics, would take the images and intuitions and physical understanding and transform them into equations. That task fell to James Clerk Maxwell. Maxwell was a Scottish physicist with a gift for mathematics. In the 1860s, he read Faraday's work. He saw the patterns. He recognized that all of Faraday's observations could be described by mathematical equations. Maxwell worked for years, refining and unifying the laws of electricity and magnetism. In 1865, Maxwell published his equations. 4 equations, elegant and symmetrical. They showed that electricity and magnetism were not separate phenomena, but 2 aspects of a single electromagnetic field. And they predicted something extraordinary. The equations showed that disturbances in the electromagnetic field would travel through space as waves moving at a specific speed. When Maxwell calculated that speed, he found it matched the known speed of light. Light itself was an electromagnetic wave. Electricity, magnetism, light, all the same, all aspects of electromagnetism. Maxwell had unified what seemed like separate mysteries into a single, beautiful theory. He died young, at 48, never knowing how profoundly his equations would shape the future. But Maxwell's equations lived on. Other scientists read them, studied them, realized they could predict the existence of electromagnetic waves of different wavelengths, waves longer than visible light, waves shorter than visible light, an entire spectrum waiting to be discovered. In Germany, Heinrich Hertz set out to prove Maxwell right. In 1887, Hertz built an apparatus that could create oscillating electrical currents. He placed a detector across his laboratory. When he activated his transmitter, the detector sparked. Invisible waves had crossed the room, radio waves, exactly as Maxwell had predicted. Hertz died young as well, at 36. He did not think his discovery had any practical use. He was wrong. Within a few years, inventors around the world were working on wireless telegraphy. Messages could be sent through the air without wires. The age of radio was dawning. But let us return to the 1870s. While Maxwell was writing equations and Hertz was still a student, inventors were trying to make electricity useful. Not just a curiosity for laboratories, not just a way to send signals, but a source of light and power for ordinary people. The arc lamp had existed for decades. Remember Humphrey Davy's demonstration from earlier in the century. 2 carbon rods connected to a powerful battery. When brought together and pulled slightly apart, an intensely bright arc of light blazed between them. But arc lamps were impractical for most uses. They were too bright, harsh, glaring. They required enormous batteries or generators. They consumed carbon rods rapidly. They were expensive to operate. They were suitable for lighting large public spaces, perhaps, factories, streets, but not homes. What was needed was a gentler light, a light that could burn in someone's home without overwhelming the room, a light that used electricity efficiently, a light that would last for many hours without maintenance, a light that ordinary people could afford. The answer was the incandescent bulb. The idea was beautifully simple. Pass electric current through a thin wire or filament enclosed in a glass bulb. The filament would heat up from the resistance. It would glow. It would emit light. If the bulb contained no air, the filament would not burn. It would just glow and glow and glow. Simple in concept, extraordinarily difficult in practice. Many inventors worked on this problem through the 1870s. The challenge was finding a filament material that would glow brightly without burning up, breaking, or becoming too expensive to manufacture. Platinum was tried. It glowed beautifully, but melted at the temperatures needed for bright light. Various carbon materials were tested. Some burned up. Some were too fragile. Some did not glow brightly enough. In England, Joseph Swan was working on incandescent bulbs. Swan was a physicist and chemist. He had been experimenting with electric light since the 1850s. By the late 1870s, he had developed a practical bulb using carbonized paper as the filament. The paper was cut into a thin strip, carefully heated in an oven to drive off volatile compounds, leaving just carbon. This carbonized paper was placed in a glass bulb. The air was pumped out to create a vacuum. Wires conducted current to the filament. Swan demonstrated his bulbs publicly in 1878 and 1879. They worked. They glowed with a warm, steady light. They lasted for hours. He installed them in his own home. He gave public lectures lit by his electric lamps. The response was enthusiastic. In America, Thomas Edison was attacking the same problem. Edison was different from Swan in temperament and approach. Edison was not primarily a scientist seeking to understand nature. He was an inventor seeking to create useful devices. And he was a businessman seeking to build industries. Edison had achieved fame and wealth through earlier inventions. The phonograph, the improved telephone transmitter, the stock ticker. He understood not just invention, but commercialization. He knew that a successful product needed more than just technical merit. It needed to be manufacturable, affordable, reliable. It needed to fit into a system. By the late 1870s, Edison had established an invention factory at Menlo Park, New Jersey. This was not a solitary inventor in a workshop. This was an organized research facility. Edison employed teams of skilled assistants, machinists, glassblowers, draftsmen, electricians. They worked under his direction, testing his ideas, building prototypes, conducting experiments. Edison approached the incandescent lamp systematically. He broke the problem into parts: the filament material, the bulb shape, the vacuum quality, the connections and seals. Each part was tested methodically. Hundreds of materials were tried as filaments: platinum alloys, various metals, carbonized plant fibers, paper, cardboard, thread, fishing line, human hair, even beard hair from members of his team. Each test was documented. What material, what dimensions, what current, how bright, how long did it last, why did it fail? The data accumulated, patterns emerged, carbon-based filaments showed promise. But which carbon? How to prepare it? By late 1879, Edison had developed a practical incandescent bulb using a carbonized bamboo filament. Bamboo was chosen after testing thousands of plant materials. Bamboo fibers were long and uniform. When properly carbonized, they made excellent filaments. A single filament could burn for over 1,200 hours. That was 50 days of continuous operation, or many months of use for a few hours each evening. Edison demonstrated his bulbs to the public on New Year's Eve, 1879 to 1880. He lit up the streets around his Menlo Park laboratory, hundreds of bulbs glowing in the winter darkness. People came from New York City and Philadelphia to witness this marvel. They walked down streets lit by electric lamps. The light was softer than arc lamps, warmer than moonlight, steadier than gas flames. It did not flicker like candles. It did not smell like kerosene. It simply glowed with a gentle, reliable radiance. For many visitors, it was the first time they had seen electric light. It seemed miraculous. It seemed like a glimpse of the future. They were right, but Edison understood something that many other inventors missed. An electric light bulb by itself was useless. It needed electricity, and electricity in a home required infrastructure, wires to carry current from some central source, a generator to produce the current, switches to control the lights, sockets to connect the bulbs, meters to measure how much electricity each customer used so they could be billed appropriately. The lamp was just one component of a system, and the system did not exist yet. Edison set about creating not just a light bulb, but an entire electrical system. He designed generators specifically for lighting, large dynamos driven by steam engines. He designed distribution cables to carry current underground through city streets. He designed junction boxes where cables branched to individual buildings. He designed meters to measure consumption. He designed switches, sockets, and fixtures. He even thought about how to price electricity. Too expensive and no one would adopt it. Too cheap and the system could not sustain itself financially. He studied gas lighting costs and aimed to match them. On September 4th, 1882, Edison opened his Pearl Street station in Lower Manhattan. It was the world's first commercial electric power station. The building housed 6 generators, each weighing 27 tons and producing about 100 kilowatts of power. Steam engines, burning coal to boil water, drove the generators. The generators were connected to a network of underground copper cables. At 3 o'clock in the afternoon, the switches were closed. Current flowed through the cables. In 85 buildings in a district of Lower Manhattan, about 400 electric lamps began to glow. Offices, shops, the New York Times building, J.P. Morgan's office, places that had previously been lit by gas or oil suddenly had electric light. The age of electric light had begun, but it was just the beginning. Just a few city blocks glowing in the dark. Just 400 lamps in a city of millions. The spread of electrical systems was not simple or smooth. Edison's system used direct current, or DC. Current flowed in one direction, from generator to customer. But DC had a problem. It could not be efficiently transmitted over long distances. Voltage would drop, power would be lost. Each power station could only serve a small area, perhaps a mile in radius. There was an alternative, alternating current, or AC. With AC, the current reversed direction many times per second. AC could be easily transformed to high voltage for transmission, and then back to low voltage for use. High voltage meant less power, lost over distance. One power station could serve a much larger area. A Serbian inventor named Nikola Tesla became the champion of AC. Tesla had an extraordinary mind. He could visualize machines in 3 dimensions, seeing every gear and wire and coil. He could run simulations in his imagination. He immigrated to America in 1884 and briefly worked for Edison. But they disagreed about current. Edison believed in DC. Tesla believed in AC. Tesla left Edison's company and eventually partnered with George Westinghouse, an industrialist who recognized the advantages of AC. The 1880s and 1890s became known as the War of Currents. Edison and his backers promoted DC. Westinghouse and Tesla promoted AC. Edison went so far as to publicly electrocute animals with AC to demonstrate its dangers. The battle was sometimes ugly, but in the end, the technical advantages of AC were too great to ignore. In 1893, Westinghouse won the contract to light the world's Columbian Exposition in Chicago. 200,000 incandescent bulbs powered by AC generators. 90,000 night visitors gazed in wonder at the illuminated White City. It was like a vision of the future, and it was built on alternating current. Even more importantly, Westinghouse and Tesla built a power station at Niagara Falls in 1895. The immense energy of falling water drove massive generators. The sea power was transmitted 22 miles to Buffalo, New York. It was proof that electricity could be generated at a central location and distributed across an entire region. The War of Currents was over. A sea had won. The 20th century would be powered by the system Tesla had championed. As the 1800s ended, electricity was transforming life in cities. Streets were lit at night. Trolley cars ran on electric rails. Elevators lifted people to the upper floors of increasingly tall buildings. Factories replaced steam engines with electric motors. Telegraph wires and telephone lines connected cities and countries. But most people in the world still lived without electricity. Rural areas were too far from power stations. Small towns could not afford the infrastructure. The electrical age was urban. The countryside remained dark. This would change in the decades to come, but slowly. Power lines had to be built across mountains and deserts. Transformers had to be installed in remote locations. Generators had to be built large enough and efficient enough to power entire regions. The early 20th century brought refinement and expansion. Engineers improved generators and transformers. They learned to transmit power over hundreds of miles. They built dams to harness the energy of rivers. They strung power lines along roads and across farmland. Governments began to see electricity not as a luxury, but as essential infrastructure. In the 1930s, President Franklin Roosevelt created the Rural Electrification Administration in the United States. Government loans helped build power lines to farms and villages. By 1950, most rural Americans had electricity. Similar programs spread across Europe, Japan, and other industrialized nations. Electricity brought more than light. It brought refrigerators to preserve food, washing machines to ease labor, radios to bring news and music into homes, televisions to broadcast images across the world, air conditioning to make hot climates bearable, computers to process information. The list grew longer every decade. Each new electrical device created demand for more power. Power grids expanded. Coal plants were built, burning fossil fuels to boil water into steam that turned turbines that spun generators. Nuclear plants followed, using atomic energy to create heat. Wind turbines captured moving air. Solar panels converted sunlight directly to electricity. The grid became a vast, interconnected network. Power generated anywhere could flow to anywhere else, at least in theory. And then there was the revolution in electronics. In 1947, researchers at Bell Labs invented the transistor. It was a tiny device made from semiconductors, like silicon. It could amplify electrical signals. It could switch current on and off. And it was solid. No moving parts. No vacuum tubes that burned out. The transistor changed everything. Radios became portable. Computers shrank from room-sized machines to devices that could sit on a desk, then to devices that could fit in a pocket. Integrated circuits packed thousands, then millions, then billions of transistors onto chips smaller than a fingernail. The same force that created lightning in storm clouds now powered devices that could store human knowledge, process complex calculations in milliseconds, and connect people across continents. Electricity became invisible, a background presence, something people expected when they flipped a switch or pressed a button. Today, in the 21st century, we live in a world Benjamin Franklin could never have imagined. Take a moment to look around you. Even in darkness, electricity is present, flowing through wires in the walls, waiting behind switches, powering devices in sleep mode, charging batteries, maintaining connections to distant networks. Electricity flows through wires in the walls of our homes. Behind the plaster or drywall, invisible networks of copper carry current from room to room. It powers lights that come on at the flip of a switch. No matches to strike, no wicks to trim, no fuel to refill. Just a switch, a motion of the finger, and light appears. It powers stoves and heaters. We cook without fire. We warm our homes without burning wood or coal in our rooms. The fire has been moved elsewhere, to a power plant, perhaps hundreds of miles away, and the energy it produces reaches us as electric current. It charges batteries in our phones and computers and countless other devices. We plug them in before sleep and wake to find them ready for another day. The flow of electrons into chemical cells, storing energy for later use. Volta's discovery, miniaturized and refined and made portable. It enables the internet, that vast network of connected devices spanning the globe. Computers in data centers, kept cool by circulating air, running continuously, routing information. Signals traveling through fiber optic cables beneath oceans. Satellites orbiting overhead. All powered by electricity, all dependent on the continuous flow of current. Modern life depends on it utterly. Without electricity, cities would go dark. Not just the lights, everything. Traffic signals would fail. Hospitals would lose power. Refrigerators would stop cooling. The food stored inside would begin to spoil. Water pumps would stop. In tall buildings, the water would drain from upper floor pipes. Elevators would cease. Phones would die as their batteries depleted and towers lost power. The internet would fail. Communication would become local again, immediate, only as far as one's voice could carry. Commerce would halt. Stores could not process electronic payments. Gas stations could not pump fuel. Factories would go silent, their assembly lines still. Offices could not function. Modern work depends on computers, on databases, on cloud storage. All of it requires electricity. The world would change in an instant. We would be thrown back, not to the 19th century, but to something far more difficult. Because unlike people in the 19th century, we have not maintained the older systems. We do not know how to function without electricity. We have not practiced those skills. We have no backup systems in place. We have built a civilization that assumes electricity will always be available. And yet, for all our dependence on electricity, most of us barely understand it. We flip switches and expect light. We know that something happens. Current flows, bulbs glow, but the details are mysterious. We plug in devices and expect them to charge. We connect to networks and expect data to flow. We trust the system without understanding it. The complexity of the grid is invisible to us. The power plants generating electricity, coal plants where crushed coal burns in enormous furnaces, boiling water into steam that drives turbines, natural gas plants operating on similar principles, nuclear plants where atomic reactions generate intense heat, hydroelectric dams where falling water spins generators, wind farms where rotating blades turn in the wind, solar arrays where panels convert sunlight directly into current. All of this feeds into the grid, a network of high-voltage transmission lines carrying power across regions, transformers stepping voltage up for efficient transmission and then stepping it down for safe use, distribution lines bringing power to neighborhoods, transformers on poles or in green boxes on the ground, making final voltage adjustments, service lines connecting to individual buildings, circuit breaker panels directing current to different circuits within the structure, and finally, outlets where we can tap into this vast network with a simple plug. All of this complexity, all of this infrastructure, all of this investment, and we experience it as simply. Electricity is available. It is a utility, a service, something we pay for monthly and rarely think about, like water from a tap or roads we drive on, background elements of modern life. But the story of how humanity learned to capture lightning is a story of centuries of curiosity, of patient observation, of countless experiments conducted by people who were simply curious about the world, people who looked at amber attracting feathers, at lightning splitting the sky, at frogs' legs twitching, and asked why. Why does this happen? What causes it? Can it be repeated? Can it be measured? Can it be understood? From the ancient Greeks walking on beaches to William Gilbert working by candlelight, from Benjamin Franklin flying a kite in a storm to Alessandro Volta stacking metal discs, from Michael Faraday spinning copper discs between magnets to James Clerk Maxwell writing equations, from Thomas Edison testing thousands of filaments to Nikola Tesla championing alternating current. Each person built on what came before. Each added another piece to the puzzle. Each brought us closer to understanding this invisible force that surrounds us and flows through us. Each contributed to the foundation upon which our modern world is built. Electricity is not captured lightning, not really. Lightning is just one dramatic manifestation of electromagnetic forces that exist everywhere, in every atom, in every molecule, in the bonds that hold matter together, in the space between stars, in the fabric of reality itself. We have learned to guide these forces, to channel them through wires and circuits, to make them serve our purposes, to convert them from one form to another, from mechanical motion in generators to electric current in wires, to light in bulbs and heat in stoves and motion in motors and information in computers. But we did not truly capture anything. we learn to work with nature, to understand the principles by which nature operates, to align our actions with those principles, to dance with forces that have existed since the beginning of the universe. The universe is fundamentally electromagnetic. Charged particles attract and repel. Fields extend through space. Energy transforms from one type to another. And consciousness arises somehow through electrical patterns in biological nervous systems. Everything we see and touch and experience involves electromagnetic interactions at some level. We are electromagnetic beings living in an electromagnetic universe. And electricity, in the modern sense, is simply our name for our deliberate, controlled use of these fundamental forces. And the story continues. Today, researchers work on quantum computing, using the strange properties of subatomic particles to process information in entirely new ways. Quantum bits that exist in superposition, neither 0 nor 1, but both simultaneously until observed. Circuits cooled to near absolute zero. Calculations that would take conventional computers millions of years completed in minutes. The manipulation of individual electrons and photons. Electricity at its most fundamental level. They work on fusion power, attempting to recreate the energy of stars in controlled conditions here on Earth. Plasma heated to millions of degrees. Magnetic fields containing the reaction. If successful, fusion would provide nearly limitless clean energy, the same process that powers the sun, brought under human control. Another step in humanity's dance with electromagnetic forces. They work on wireless power transmission, imagining a world where electricity flows through the air without wires. Nikola Tesla dreamed of this over a century ago. He built towers designed to transmit power wirelessly across continents. His dream was not realized in his lifetime, but research continues. Small devices now charge wirelessly. Perhaps larger systems will follow. Perhaps one day the tangle of wires and cables will disappear, replaced by invisible streams of energy flowing through space. They work on room temperature superconductors, materials that conduct electricity with zero resistance at ordinary temperatures. Currently, superconductors must be cooled to extremely low temperatures to function. But if room temperature superconductors can be developed, power transmission would become vastly more efficient. No energy lost to resistance, no heat generated in power lines. A revolution in how electricity moves through infrastructure. They work on more efficient solar panels that convert larger percentages of sunlight into electricity, that work in low light conditions, that can be manufactured cheaply, that can be integrated into building materials, windows that generate power, roof tiles that capture the sun's energy, roads that produce electricity while vehicles drive over them. They work on better batteries that store more energy in less space, that charge faster, that last longer, that use sustainable, abundant materials rather than rare metals. Batteries that could store enough solar or wind energy to power homes through the night. That could make electric vehicles truly practical for everyone. That could stabilize entire power grids. The future of electricity is not yet written. The path forward is not predetermined. But the direction is clear. Toward cleaner generation. Toward more efficient transmission and storage. Toward deeper integration with our lives and devices. Toward a fuller understanding of the electromagnetic nature of reality. Perhaps one day we will generate all our power from renewable sources, wind and sun and wave and and geothermal heat, perhaps fossil fuel plants will be historical curiosities, places our grandchildren visit to see how people once generated electricity. They burned ancient compressed plants to boil water to spin turbines, the tour guide will say. And the visitors will shake their heads in wonder at the indirect inefficiency of it. Perhaps we will store energy so efficiently that power plants can be switched off when not needed. No need to run generators continuously. Just charge massive battery systems when the wind blows and the sun shines. Then draw from those reserves when demand is high or generation is low. Perhaps we will learn to transmit power without loss, without the need for extensive networks of metal wires and transformers. Perhaps electricity will become more like water in some ways. Abundant, available, essentially free once the infrastructure is built, the cost being only in the maintenance of the system. Or perhaps something entirely unexpected will emerge. Some new understanding of electromagnetism, some new application we cannot yet imagine, some breakthrough that makes our current technology seem as primitive as a Leyden jar seems to us now. The history of electricity teaches us that progress comes from curiosity, from asking questions without knowing where the answers will lead, from careful observation and patient experimentation, from building on the work of others, from sharing knowledge freely, from being willing to fail repeatedly in pursuit of understanding. The lightning that split the skies above ancient peoples is the same electromagnetic phenomenon that powers these words you are hearing now. The electrons flowing through the device playing this audio are the same particles that exist in every atom of your body, the same charges that make amber attract feathers, the same currents that made Franklin's key spark in the storm. Across thousands of years, we have not changed the fundamental nature of electricity. We have only learned to see it more clearly, to understand it more deeply, to use it more wisely, to work with it rather than simply fear it or worship it. Perhaps that is the real lesson. That understanding leads to capability. That curiosity leads to discovery. That patience leads to progress. That humanity's greatest strength is not our physical power, but our ability to observe, to think, to question, to experiment, to learn, to build on what we learn, and to share that knowledge with others who will carry it forward. As you drift towards sleep, imagine the electric currents flowing through your own body. Your nervous system is an electrical network. Signals travel from nerve to nerve as ions flow across cell membranes. Your thoughts are electrical patterns. Your heartbeat is triggered by electrical pulses. You are, in a sense, an electrical being, connected to the same forces that Benjamin Franklin drew from the storm, the same forces that light the world. Rest now in this understanding. You are part of the electromagnetic universe. Every atom in your body contains charges. Electrons orbit nuclei. Fields extend through space. You are never separate from electricity. It is woven into the very fabric of your existence. Let this thought be a comfort as you sink into rest. You are connected to everything, to the history of discovery, to the scientists who wondered and questioned, to the force that animates the stars and powers your cells. Breathe slowly. Feel the rhythm of your heart. Know that electrical signals are traveling through you even now, keeping you alive, maintaining the delicate balance of your body. The story of electricity is, in the end, your story too. Thank you for listening with Sleepy Facts. Let your breath steady. Let your thoughts grow quiet. Rest smarter by allowing your mind to settle into the rhythm of night. If you enjoyed this moment of calm, you are welcome to subscribe. And if there is a topic you want to hear next, simply leave it in the comments. Wishing you a peaceful night and gentle dreams.